The intention of this video is to learn that new way of representing electron configurations for people that have trouble visualizing what exactly we're talking about. It also introduces our next quantum number, which is what we call the magnetic quantum number, which we represent with the variable m with the subscript L. This quantum number also explains why electrons form pairs, which was one of the problems we had with Bohr diagrams. Now, electrons form pairs because of something that we call orbitals. Orbitals, remember, are distinct from shells or the orbit layers that we see within the old Bohr diagrams. And magnetic quantum numbers describe orbitals, which are a component or a part of a subshell, and each orbital within a subshell holds 2 electrons, which again explains why electrons form pairs. Now, the easiest way for us to visualize what orbitals and indeed what subshells are is to actually try drawing them. So we start with the simplest elements that only have S subshells: hydrogen, helium, lithium, and beryllium. Let's start by remembering the electron configurations for all of them. Hydrogen is 1s1, helium is 1s2, lithium would be 1s2, 2s1, and beryllium would be 1s2, 2s2. Now, we remember that the S subshell can only hold 2 electrons, and we remember vaguely that the S can be used to help us remember the shape of the subshell, which is a sphere. So we start, when we want to draw subshells and orbitals, we start with this tiny point here, and this point here is the nucleus. We remember from Ernest Rutherford's experiment that 99.9999999% of an atom is actually empty space, and that empty space is the subshell, which, again, we know that the S stands for sphere, so what I have drawn here is the 1s subshell, the 3D space in which hydrogen's 1 electron can be. So that 1 electron is somewhere in there. But if we remember the Heisenberg uncertainty principle, is it possible for us to know exactly where electrons are? So that answer is no, which is why if you draw that there's 1 electron floating around here, that's technically incorrect because we don't know where that electron is. All that we know is that it is somewhere within this space here. Now, if we draw helium, again, here's the nucleus, and then here we're drawing the 1s subshell. Now, again, this looks exactly the same as hydrogen. It's the same spherical 3D space, but this time instead of 1 electron, this time somewhere in there are 2 electrons. Again, we don't know where they are, but we know that there is a high probability that they are somewhere in this space. Now, we know that an S subshell can only hold 2 electrons, so when we get to lithium and beryllium, we start by drawing the nucleus, then here is our 1s subshell, but lithium needs a second S subshell at a higher energy level, which means that this second sphere, in quotes, that I'm drawing, this is the 2s subshell, and again, lithium's 2 1s electrons are somewhere in the 1s subshell here, and the 1 2s electron is floating somewhere around in here. Again, we don't know where they are, but they are somewhere there. Beryllium would look exactly the same. Here is our 1 nucleus with the 1s subshell and the 2s subshell. Only difference, beryllium has 2 electrons floating in here. Now, we remember what an orbital is, that an orbital is a component of a subshell that holds 2 electrons, which means that the S subshells that I have drawn here can also be called S orbitals, because an orbital is a part of a subshell that holds a pair of electrons. So each 1s subshell has one orbital, one part that can hold a pair of electrons. Now, orbitals become easier to understand when we start looking at elements that have a p subshell. So if we write the electron configurations for boron, carbon, and nitrogen, boron would be 1s2, 2s2, 2p1. So let's go ahead and draw the 1s and 2s subshells. Here's our nucleus. Here is 1s. And here is 2s, so that takes care of 4 of the electrons. But what do p subshells look like? Well, a p subshell, at least part of a p subshell, looks like this. In 2D, these kind of look like propeller blades. Some people, when they look at p subshells in 3D, think that they look like hand weights or dumbbells. And in beryllium's case, this is part of the p subshell, and that part has 1 electron that is floating around somewhere in here. Now, I said part of a p subshell because this part of a p subshell is actually a p orbital. This is only part of the subshell, and it can hold a maximum of 2 electrons within it. If we want to see what an element looks like that has more than 1 p orbital, we can look at carbon and nitrogen, which are 1s2, 2s2, 2p2, and nitrogen is 1s2, 2s2, 2p3. Now remember that electrons don't want to stay together. They repel each other. So the only time that we want electrons to pair is if there is no other choice. So let's start by the same way. Draw the 1s subshell outside of the nucleus, then 2s, then here is a 2p orbital, and 1 of carbon's electrons are going to be in there, and then here is a second p orbital where carbon's second electron is going to be. So each of these is a separate p orbital, and you can kind of predict what the names of each of these is going to be. We see that this p orbital is vertical, so this is what we would call the py orbital, and this second p orbital here, this is what we call the px orbital. So the reason why we have 2 p orbitals but only 1 s orbital is the p orbital can hold 6 electrons. We know that an orbital can only hold 2 electrons maximum. 6 divided by 2 means that we need 3 separate orbitals for the p subshell, py and px. And if we draw nitrogen, we can see where the third p orbital is. Let's start with the nucleus. Here's 1s. 2s, here's the first p orbital, here is the second p orbital, and here is the third p orbital. So again, nitrogen has 3 electrons. Since electrons do not want to pair unless they have no other choice, 1 electron goes into py, 1 electron goes into px, and if you said that this is what we call a pz orbital, you would be accurate, and the third electron goes into pz. Now, again, let's just codify this rule. When adding electrons to p subshells, each orbital must have at least 1 electron before electrons can pair, because electrons repel and they don't want to stay together unless it's absolutely necessary. So, for that reason, if we take a look at each of these, oxygen, fluorine, and neon, we can draw the subshells and orbitals relatively easily. 1s, 2s, and just like with nitrogen, how all of its p orbitals have at least 1 electron present, here's 2py, 2px, and here is 2pz. The only difference here is that while 2 of the orbitals will only have 1 electron, because oxygen has 4 electrons, that means we need to actually start pairing electrons here. So one of oxygen's orbitals is actually going to have 2 electrons in it. 2 plus 1 is 4. But again, we can't see electrons, so the orbital drawing looks exactly the same as nitrogen. If we do the same thing with fluorine, 1s, 2s, 2py, 2px, and 2pz, again, the only difference now, even though one of fluorine's orbitals, p orbitals rather, only has one electron in it, two of them now have two electrons. 2 plus 2 plus 1 is 5. And then finally, neon, as you can predict, 1s, 2s, 2px, 2py, 2px, and 2pz. And because all of neon's orbitals are full, that means that each of the p orbitals, pz, px, and py, will all have two electrons in them, showing that each of these orbitals is necessary, because that is actually what allows electrons to pair, because each orbital can only hold two electrons maximum. But again, we cannot see these electrons, and because we can't see these electrons, the orbital drawings for oxygen, fluorine, and neon look identical, because we cannot see how many electrons are contained within each. To test your ability to recognize what subshells mean and connect electron configurations with orbital drawings, there are 3 orbital drawings that act as challenges for you. So can you draw the orbital drawings for silicon, chlorine, and potassium? And as a hint, remember, if we have 1s, a 2s subshell is just an S subshell that is farther away from the nucleus, and that theoretically also applies to P subshells as well. In the next video, we're going to be looking at the last quantum number and completing the puzzle about how the quantum notation system works.